Hey everybody, and welcome to another Learning Statistics with Jamovi video. How do I do a one-way ANOVA with a between subjects variable? That's what we're going to be doing in this video. One-way ANOVA, so that one-way means here one independent variable with three or more levels, okay? And these levels are all independent groups. So that is, there's no overlap or no multiple measurements on my DV, on my dependent variable, for any person in any of the groups. They only get one group. They only get one change, one intervention, and we compare those changes, manipulations, or interventions with the other 2, 3, 4, 5, 6, however many interventions, changes, manipulations that you do have. Okay, so that's the only thing. We have one manipulation, one independent variable, and we're trying to see whether or not those things cause a change in my DV, a change on my DV. That's what we're doing today. Before we get started into the data, I am using the most recent Mac version of Jamovi, 2.3.3. Okay, so if you want to follow along with me, please update your Jamovi. Just make sure that we have the most updated version. You know, I do these videos every so often because things change in Jamovi, and I want to make sure that, you know, we all have the most appropriate tools. So if you are somebody who's watched my previous Jamovi series or other statistics program videos like JASP, JASP, you know, you can follow along here more easily with the versions that you can download now. All right, so let's open up some data. Again, we are using the Learning Statistics with Jamovi data sets. You add this via the module. Okay, we click that open every once in a while, every so often in videos. I do this. We go to the Jamovi library. You can see that I need to update a whole bunch of stuff. I just haven't gone around to it. But what we are looking for, and I think it's like about halfway down, we are looking for the LSJ-data. There it is, Learning Statistics with Jamovi from Danielle Navarro and David Foxcroft. You can click on this link here to take you directly to the webpage where they have the book. Free PDF available, and it has all that information. I already have it installed, of course, as you saw. So we are going to open, and you can see that I already have the data library open and ready to go for the LSJ data. So we are going to use the canned data that they created for the clinical trial. So they have two clinical trial data sets. We are going to use clinical trial, and you can use the clinical trial 2 if you wanted to see what they did for binary contrast. So we're not going to do contrast just yet in this video. So we could do that in another video. I do want to do a contrast video with this soon. So stay tuned for that. The other clinical trial 1 from chapter 14 also includes a second independent variable, which I don't want to, if you're not familiar with ANOVA, I don't want to overwhelm you with all of these variables that we aren't going to be using. So we're going to use the original clinical trial, and this is what you can use for the descriptive module in chapter 4, and then 13 and 14, which is one-way ANOVA and factorial ANOVA, I believe, in their book. So let's talk about ANOVA, and then we'll do some post-hoc tests with this one. So let's open up clinical trial. So as I said, if you want to follow along, this is how you do it, okay? All right, so this one does have a second variable of therapy, but we're going to ignore that one. We are going to use the drug. We're going to ignore therapy, so I'm going to just delete the variable. So we don't concern ourselves with it at all. Now, of course, you're welcome to delete it. You're welcome to keep it in there and just ignore it. But that is what we are going to be doing in this particular video. And so here we have 18 people who've received one of 3 pill form drugs in a clinical trial. Now, the people who received what you can see as the placebo didn't know that they were taking a placebo. But then we have Anxi-free, which is, I suppose, a play on an anti-anxiolytic or an anti-anxiety drug like Xanax, for example. So Anxi-free. So we're going to compare that drug to a placebo, a sugar pill, which has no active ingredient, no psychoactive substance, unless you consider sugar to be a psychoactive substance. But, I mean, sugar is needed everywhere in the body, so there's that. And then we have a third drug called Joyzepam. Okay, Joyzepam, a play on other kinds of drugs like citalopram or escitalopram, which are antidepressants. These are SSRIs, okay? And so the idea here is we are comparing a antidepressant to an anti-anxiolytic or anti-anxiety drug to a placebo, and then we are going to measure their mood gain. So this variable is not what their mood is, but actually a difference score. And we are going to assess their gain in mood from some pre-test. They've taken the drug for a number of weeks, and then they take this post-test on, I don't know, the Beck Depression Inventory, or the CESD, the Center for Epidemiological Study Depression Scale, or whatever depression scale that you have. And so we're going to try to see whether or not depression can be managed by a placebo, a anti-anxiolytic, which doesn't really change brain chemistry in the sense of long-lasting changes, but it just sort of masks, it sort of calms you down. It doesn't get rid of anxiety, it just calms you. And then an SSRI, which is meant to boost the amount of serotonin in your brain. So as a neurotransmitter. So that's what we're going to do for this particular one. So how do you do a one-way ANOVA? Well, there are two ways to do a one-way ANOVA in Jamovi. I'm going to do both of them, and I'm going to show you the differences between the two. They're not the same module. And in many ways, one is deficient for the other, or to the other, I should say. So let's do what we are thinking about, which is a one-way ANOVA, and let's use the one-way ANOVA module, and then we will use the just ANOVA module and see how they compare and contrast. So let's do the one-way ANOVA. Let's plop this open. Okay. So the one-way ANOVA module allows you to do several tests at the same time because it says dependent variables. So you can put as many DVs in here as you want, as long as you are doing this, as long as you are assessing them on the same grouping variable, your independent variable. As long as you do that, you can do as many DVs as you want, okay? So we're going to go ahead and put mood gain in the dependent list. And before I put the grouping variable in here, I want to go through these options, okay? So the first thing is first. For some reason, the don't assume equal variances option is checked. I don't know why this is the case, and I think it should be the exact opposite. So just keep that in mind that when you add in this, it's going to be Welch's ANOVA, okay? So, or Welch's F, as opposed to Fisher's F, okay? So we're going to uncheck that, and we're going to assume that we have equal variances, okay? And that's this assumption check here, a homogeneity of variance test. So we're going to click that, and we're going to see whether or not we do. Now, you could, in fact, have both of these on. And sure, why don't, instead of doing that, we'll get Welch's and Fisher's on there. But just be aware that Fisher's ANOVA, or Fisher's F here, is the parametric version, and Welch's is the non-parametric version. So you need to be aware of that. So if you were to report an ANOVA in a particular way that was requiring the F test, you want Fisher's, not Welch's, okay? So Jamovi devs, please assume equal variances as the default as opposed to the opposite. So we want our homogeneity of variance test, which is Levine's, okay? And then we also want our Shapiro-Wilk, which is going to test whether or not the mood gain DV is normally distributed with our 18, I think it was 18 data points. So just keep that in mind. Missing values, I said in a previous video that I always prefer the cases analysis by analysis. And in this case, if you have multiple dependent variables, you want to include the cases or the people, the rows, as it were, of the data set as much as you want. So if we had multiple dependent variables in here, we wouldn't want to exclude everyone who had only one missing value, but only exclude the people that have a missing value in the variable that I'm interested in for that particular test, if that makes sense. In any case, that's what analysis by analysis means, as opposed to excluding cases list-wise. Let's go ahead and grab our descriptive table and our descriptive plots too. Now, Post-Hoc, we have limited options here. We have limited options. So the Post-Hoc test is either none, the game's howl. So if you have Welch's F, you are going to grab the game's howl, unequal variances. And if you are going to use Fisher's, then you are going to use Tukey's. So I'm just going to grab Tukey. This is Tukey's LSD. Least significant difference is what the LSD stands for, okay? And as far as statistics goes, we are going to grab our mean difference for this test. We are also going to get our p-value. I wish this just said report p-value. We are also going to do the t-test. We're going to show the t-value and the degrees of freedom. And for shiz and gigs, let's just grab flagging comparisons that are below our adjusted, which is what the Tukey test is going to do, below our adjusted 0.05 alpha value. Okay, let's drop in our drug here. Now, one thing to note is that drug is technically a text-based nominal variable. And I said this in a previous video, but as long as your text-based nominal variables are spelled the same, we can use it as a nominal variable and it's fine. We don't actually have to create numerical levels for this because it's reading the fact that there are three things that are spelled differently: Angzifree, Joyzepam, and placebo in alphabetical order. It is finding those. Now, if I accidentally spelled Joyzepam wrong in one of these cells, it will put that in as a fourth level. So this is a good way to check if you've got everything set. And you don't, like I said, you do not have to make a dummy code like 1, 2, and 3 or anything like that for this. You can just leave it, even though it's a nominal text variable. It's still good. It's all good. So let's go back to analyses. Click on our one-way ANOVA and drop in drug. So I just dragged it, but you can use the arrow. You can double click it and it'll go to the right place. And again, even though it's a text variable, it still works with the Venn diagram nominal variable. All right, let's go through the output sort of quickly so I can compare it with the other ANOVA module in this video. Okay, so as we can see, Fisher's test, if we assume we have homogeneity of variances, and we do. We have a low F for the Levine's test, which means our p-value is above our criterion for our assumption checks. This means we have not violated Levine's test for homogeneity of variances. That means our variances for each of these three groups is relatively equal on mood gain. Okay, and you can kind of see what I mean here. If we look at our standard deviation, okay, which is the unsquared version of variance, which is what this is testing. Okay, so we have 0.39, 0.21, 0.28. Now, you know, it's about a 0.2 spread, I would say, a little bit less than that, 0.18 or so range, and that's within equal parameters there. So we can assume that with these standard deviations and these variances for 6 anxiety-free patients, 6 joyzepam patients, and 6 placebo patients in this clinical trial, that we have we have passed that assumption. We have not violated that assumption. Just briefly here, the Shapiro-Wilk test for mood gain, relatively close to 1 for W there, which means the p-value is quite high, very similar to some of the other tests that we've done previously. And so we have not violated mood gain being a non-normal or skewed, even with only 18 cases. So that's good. We've passed both of our assumptions, which means we can ignore this top line of the ANOVA source table. We can ignore it. Now, the one-way ANOVA source table looks pretty basic, and that's because it only gives you the F, the 2 degrees of freedom, and the p-value. It's essentially just a cut-down version of an actual source table, which includes sums of squares and mean squares. And this is really the only information that you need for an APA F test. It's the only thing you need. But there's something missing very crucially in this, which is that we don't get the option for an effect size. So we don't know how big this effect is. It's significant, less than 0.001. It's significant, and quite a bit significant with an F of 18.6. That's quite the difference there. And degrees of freedom of 2, 15, 2 in the numerator, 15 in the denominator. How did I get that? Well, the numerator, DF1, is K minus 1, where K is the number of groups that we have. So we have 3 groups. 1, 2, 3, anxiety-free, joyzepam, placebo, respectively. So we do N minus 1, or K minus 1, and we get that. Okay. And then degrees of freedom 2 is total N. So we have 18. So this is the denominator degrees of freedom. We have 18 minus K. So 18 minus 3 is now what we're looking for, right? So 18 minus 3, 15. There we go. Bada bing, bada boom. Now, Welch's, you can see that degrees of freedom 2, the numerator, has to be adjusted, and we get this weird decimal value for that. And that's because the assumption of the violating the equal variances assumption has to create an adjustment in the denominator to unbias what the variance of each group is doing. So if you have one of your levels of your independent variable, it just has a super big variance, it's going to bias the outcome of the F. And so to make sure that we're getting an appropriate p-value, we have to reduce the degrees of freedom in the denominator so that we are not biasing the F statistic too much. You can see this F is gigantic for Welch's. Okay, so just be aware of that. But because we did not violate homogeneity of variance, then we can ignore that. And so I'm going to uncheck it just so it gets out of here. Okay. All right, so that is, and then we have our means and standard deviations and standard errors here in our group descriptives. Okay, so the average ANSA-free mood gain was 0.71 or 0.72 if I were to round. The average mood gain for joyzepam was 1.48, and the average placebo mood gain was 0.45. That's important. That is important. So we are going to see in our post-hoc test what's driving the effect. I'm sure you can figure it out just by looking at this graph, but what was the most successful drug in this clinical trial? Maybe it was the antidepressant doing the thing that it was supposed to be doing, right? So yes, that is what we get here in our post-hoc test. So this is our Tukey LSD adjustment to our multiple comparisons test. The reason why we do this is because if we were just using our original alpha, we actually run the risk of inflating alpha by doing multiple t-test comparisons, independent samples t-test comparisons. And so for this particular one, what we are going to see in this table is the level on the left here. Okay, so here we have ANSA-free because it's alphabetical order, so ANSA-free goes first. And it's going to be compared in sort of a correlation matrix version to joyzepam and the placebo. Okay, and you can see here that ANSA-free is significantly different from joyzepam, but not, because the asterisks here show me that it is significantly different down here, note. So two asterisks. It's actually less than 0.001. You can see that there's my actual p-value. Okay, but it's not different from the placebo. Okay, so the mean difference here is 0.77. Mean difference here is 0.27. It's quite a significant difference here. Joyzepam, now compared to the placebo, because we already did Angza-free, is also significant. And this is quite a bit different, right? As you can see here, quite a bit different up on the plot. And so that's got 3 asterisks. And so that is significant at the p is less than 0.001 level. And of course, it's not, for sake of precision, not being stupid, we have less than 0.001. Now, you don't see anything down here for the placebo because it's already been compared to the 2. So that is the one-way ANOVA module for a one-way ANOVA. But let's do, like I said, let's do the other ANOVA module and see how much more information you get. And let's compare the 2, okay? The numbers and the outcomes are going to be the same, right? Because we're doing the same ANOVA. It's really all about options in this case. Now, you can see the difference here already. Even before I open all of these, we have far more options here. Instead of multiple dependent variables, we're actually only going to get one. We can only do one. But for fixed factors, we can put in multiple ones. And this is how you do a factorial ANOVA, which will be in another video. We're not going to do that right now, but we can put more than one fixed factor in here. So we're going to put our drug in here in just a second, but I do want to set up some of this information before we get started. All right, so let's go ahead and grab our options to make sure that we have everything we need to make an accurate conclusion about these data. So I want to go ahead and grab the overall model test. Oh, no, I don't want to grab the overall model test. But I do want to get my partial eta squared. That's eta. This is eta squared and partial eta squared. I'm going to grab both of them just to show you that if you were to do a factorial ANOVA, partial eta squared is better than eta squared because eta squared is the full effect and partial eta squared is just that particular variable. So we're going to go ahead and do both. And you're going to see when we have a one-way ANOVA that they're exactly the same. Omega squared, lowercase omega, as opposed to the one that you're probably familiar with, lowercase omega squared is, generally speaking, a comparable to partial eta squared and usually left for repeated measures ANOVA, although generalized eta squared is actually the preferred effect size measure for repeated measures these days. So, things are changing. I learned that this was the effect size for it, but, what are you going to do? All right, model, unless you have specific things to add here, though, let's go ahead and add in our stuff here. Unless you had specific things to change, I wouldn't change these. Sum of squares types. Type 3 is the one that you see most often. It is the least bias corrective. So if you know that you're going to have a bias in your variances, then you want to use type 1 or type 2, where type 2 is some bias correction and type 1 is even more bias correction. So type 3, no bias correction, but that's okay. Most of the time, ANOVAs are robust to this bias correction in the type of sums of squares. Now we're going to collapse that. Let's do assumption checks. Let's get our Levines and our Shapiro-Wilk tests. Let's talk about these very quickly because they're the exact same as we saw above. Okay, and you can see if you want to compare to these two, they're in a different order, which is not very nice, but okay, whatever. We're going to do that. We are not going to do contrasts, but you can. I'm going to do another video on contrasts coming up on the channel. Post-Hoc test. Now, you can see here, we have a ton of options for our Post-Hoc test. I'm going to grab Tukey so you can see, but you can see here that we can do a no correction Post-Hoc test. If you've, for example, pre-registered your Post-Hocs or your Post-Hoc pairwise comparisons, then you don't actually have to do a correction because you've pre-registered them. You've told other people that these are planned comparisons that you plan to do redundantly, and then you don't actually have to bias correct. You don't have to make sure that alpha is going to be inflated because you already said, I'm going to do these even before you collected your data. That's for pre-registration. You're not going to, we didn't do that for this particular one, so we can't do that here. I'm going to leave Tukey up so you can see how that works, but I'm also going to put Shafei, which is a more conservative test than Tukey. Okay, and then I'm also going to put Bonferroni. Very rarely do people report the Holm test. I feel bad for Holm, but very, very few people. These are people's last names, by the way. And the great news about the Post-Hoc test is that it puts them all in the same place here. What these are doing is adjusting alpha in the particular way that these statisticians said that, that alpha should be adjusted. So you're going to see when we go through them that they're slightly different. Not always. And when we get less than 0.001, it's not, there's nothing different about them. Maybe the values might be different, but probably not. But then the great news about these pairwise comparisons in this particular module for ANOVA is you can get Cohen's D for the pairwise comparisons and then get the confidence interval. So I think that's incredibly important here, and which is why I like this. So that's the Post-Hoc test. You got to make sure that you put your variable over to the right. Now, the last one that I want to get is the marginal means. Now, you're not going to see very much difference between the marginal means being in this graph versus this plot. But what you can change in this plot versus this plot is the error bars, and we are going to change them to standard error. And look how much smaller they get. And you can clearly see that joyzepam is significantly higher than anxiety and placebo on mood gain. The other thing that I like getting from marginal means, though, is the marginal means table. And these are the values that you would plot. Now, these are the exact same values that you would get in the descriptives table up here. As you can see, they're the exact same values. So you can get them in either case, right? The standard error, on the other hand, is the exact same for these marginal means as opposed to what their standard errors are up here. Okay, so just be aware of that. You can see these error bars are the exact same size. Okay, and this is the 95% confidence interval for the mean. Okay, which I also like getting because you don't get that. You don't get that up here. Okay, I mean, these are all estimates, so having confidence intervals is really important, right? So we're gonna close that, and then the last thing you can do is you can create a column for the residual values in your data set. We're not gonna do that here. Okay, so let's compare. Let's compare. Let's look at ANOVA here. And here we have an actual source table with sums of squares and mean squares with our residuals. Okay. F and P are the exact same. Our degrees of freedom are the exact same numerator, denominator. But now we get our effect size here. So this is an incredibly strong effect, 0.71 for partial eta squared, which honestly is the same representation as R squared. So 71% of the mood gain is attributable to the drug variable. Okay, which one is that? Well, then we would need to go into our Post-Hocs. And so here we get a slightly more condensed table, which is longer than it is, which is wider than it is longer, I guess. We get the same mean differences that we got up here. Oops, where is it? Right here. We get the same mean differences, okay? Anxiety to joyzepam to placebo, and then joyzepam to placebo. Still only 3 tests. And then we got our mean differences, our standard errors, the degrees of freedom for this, the t-values, which are the same t-values as up here, these 3 t-values, okay? And then we get our 3 tests. So Bonferroni, right in the middle. Tukey is a little bit more liberal than Bonferroni in this case, and then Chaffee is a little bit more conservative than Bonferroni is, although Bonferroni is a little bit starker on anxiety to placebo. It doesn't really matter which one you use. Honestly, in my opinion, it doesn't really matter which one you use. It only depends on what you feel comfortable talking about in the results section, okay? If you're doing something like this, okay? I usually use Bonferroni. I think it's the cleanest one. It has the easiest explanation. It's literally alpha divided by how many tests you plan on doing. It's the simplest way. It's the simplest one to explain. And so that's the one that I use in my classes. All right, let's take a look at these Cohen's D's. They're gigantic. All 3 of them are gigantic. So you can imagine that anxiety can possibly do a better job at increasing somebody's mood. I mean, if it's masking your anxiety, of course your mood is going to increase if we had more people, because this Cohen's D is gigantic. It's not as gigantic as joyzepam is to placebo, but it is pretty big. Now, anxiety to joyzepam is also really big, and that's because joyzepam, as an antidepressant, is meant to increase somebody's mood, right? It's doing its job in this clinical trial, okay? And it's doing its job far better than the placebo, which is important. And then we get our marginal means down here. So you can see that's how you do a one-way ANOVA in Jamovi, by the way. You have 2 options. It really depends on the simplicity of the options or the fullness of the options. Do you just want the basic information and move forward? Or do you want more information, more granular information, the ability to do contrasts or do more complex model changes or, you know, other get more information on your post-hoc test? It really depends. No effect sizes for the one-way ANOVA module, all of the effect sizes for the ANOVA module. If you have any comments, suggestions, or feedback, please leave those down below. Thank you for watching this video. Bye.